Welcome back to differential equations. In this video, I want to talk about the Laplace transform. The Laplace transform is a tool which we can use to change a differential equation into an algebraic equation. And then once we solve that algebraic equation, usually a polynomial, sometimes involving rationals, then we can use the inverse of the Laplace transform to go from the algebraic solution to the solution to the original differential equation. If that sounds too good to be true, that's because it really is. I'm going to show you, as an introduction, how we can use the Laplace transform to solve differential equations of the type that we've already talked about. And what you're going to find is that it's not worth it. It is definitely a more complicated and more involved method than the techniques that we've already discussed for solving differential equations. It does have two distinct advantages, though. After we get comfortable with the idea of the Laplace transform, I'm going to move onward and introduce two new concepts: a new operation we can perform on functions called convolution, and a new function, or maybe a function. I'll talk a little bit more about that later on. The Dirac delta function is a source of argument and frustration amongst mathematicians because it doesn't really behave the way we want a function to behave. But physicists and engineers have been using it for nearly a century now without any complaints, so I guess whether it's a function or not, it should still be something we know how to work around. The Dirac delta function is a tool for modeling impulse. What happens if instead of having a driving function, you have some impact, right? Imagining the mass on a spring system. If you have a mass on a spring and you hit the mass, causing it to start oscillating, how do you model that? The answer is the Dirac delta function. Convolution is a tool that's very important in electrical engineering and signal processing. It gives us a new way to think about the interactions between functions, and a tool that in some ways acts as an average. It's also very useful and valuable in some work involving probability and statistics, which is a little bit beyond what we want to get into in this course. So after we're comfortable using the Laplace transform and using the inverse of the Laplace transform, I'm going to introduce these two other ideas, and those are really where the Laplace transform is going to shine. These are things that differential equations doesn't really have a good way of dealing with other than using the Laplace transforms. All right, so keeping our eye on the prize, we're going to go through. We're going to find that the first couple of examples are a slog. They are a lot more challenging, and you're going to be asking yourself, why can't I just use the methods we used before? The answer is that you could use those methods and they absolutely would work and they would be better. But learning this method will unlock the door to these two new ideas that we'll get to a little bit later on. So let me get my head out of the way and let's get started. The first thing that I want to do is look at a couple of limits. The limit as x approaches infinity of e to the x times x to the negative n power. You should use L'Hopital's rule to analyze this. E to the x, as x goes to infinity, is going to tend towards infinity. And x to the negative n, as x goes to infinity, is going to tend towards 0. So this is an indeterminate form. Instead of going through and dealing with L'Hopital's rule and working through the process like that. Instead, I want to think about this using power series. You may remember from your study of calculus that the exponential function e to the x can be written as the sum n goes from 0 to infinity of x to the n divided by n factorial. Although I suppose because we already have an n in the problem, it would be more useful to us to use a different letter like k. And so when you think about this x to the negative n, sure, it will subtract off, and you'll have negative powers on the first couple of terms. But there are infinitely many terms here, which means that there are infinitely many, although the only thing that matters is there's at least one term that is going to have x to some positive power. Right? Your factorial, 1 over some constant a, times x to the negative k power for something k, is going to go to 0. And no matter what your factorial is, 1 over that factorial times x to some positive power, k, is going to go to infinity. And because this summation has infinitely many terms in it, there must be at least one, and in fact, infinitely many of them, where when you take this product, it's going to give you x to some positive power. And that positive power is going to go to infinity, and it doesn't matter how many times you add 0 to it. The limit as x goes to infinity of e to the x times x to the negative n is infinity. If I switch the signs sign on those exponents, the limit as x goes to infinity of e to the minus x times x to the positive n power, well, the same logic applies, but in the other order. If I think about e to the minus x, that's 1 over e to the x, so it's 1 over the sum. K goes from 0 to infinity of x to the k over k factorial. Now, I have infinitely many terms in the denominator of this fraction. So it doesn't matter that I'm going to multiply in the numerator by some x to the n. There are infinitely many, but all that matters is at least one powers of x in the denominator. So this is going to go to some 1 over x to some other power. I'll call it alpha. It doesn't really matter. Which is going to tend towards 0. Again, if you're not convinced by that, you can go back and look at L'Hopital's rule and look at the ways of dealing with limits in indeterminate forms, and you'll get the same results. Thinking about this in terms of power series allows us to shortcut a lot of those. Plus, it allows us to remind ourselves that power series are a thing that we've talked about at some point in the past. I don't want to have to think about the limits any further. I just want to know these results. And they are going to be important to us because the properties of the Laplace transform are going to be built around exponential functions going towards infinity. The Laplace transform is the most common example of what's known in general as the class of integral transforms. There are several others that use different kernels, but the idea of an integral transform in general is we're going to take something that combines two different functions or two different variables, in this case, s and t. That's usually the case. And we're going to integrate over the variable of the original function. And when we do that, we're going to get some new function that no longer has t, because we're taking a definite integral over t, which means we're going to evaluate this function at every possible value of t, but every time we're going to involve a new variable s. So the result is a function of s. Sometimes you'll see the idea of a transform, like the Laplace transform, talk about taking a function in t space and mapping it into a function in s space. Speaking again generally, a transform like this is taking a function in one variable and turning it into a function using a different variable. It's something that is useful in a lot of different applications in mathematics. In this course, the only transform we're going to work on is the Laplace transform. So I don't want to go into too much more detail, but I did want to at least mention that our book goes into quite a bit of detail as to what a transform is and what an integral transform is. But if we look at this expression, if we look at this, and maybe I'll rewrite the integral to get rid of all of the notation I've drawn on top of it, we're taking the integral from 0 to infinity of e to the minus st times f of t dt. And in order for us to evaluate this integral, it is important to know that the integral is going to be defined. And that's where those limits come in. If I plug in t equals 0, I will get e to the 0, which is 1. I'll get f of 0, which is something that depends on the particular function. But assuming that f of t is well defined, then I can perform that evaluation no problem whatsoever. When I take t equals infinity, or the limit as t goes to infinity, well, e to the minus s times t, e to the minus infinity, times f evaluated at infinity. And here's where we have to make some assumptions. If we assume that we can approximate the function f of t as something that is at worst polynomial, at worst t raised to the n power, then using the limits we just talked about, that will be finite. And we will have an integrand, an argument of the integral that is finite everywhere, and we don't have to worry about anything weird happening. So as a quick example, let's evaluate the Laplace transform of a simple function like t. Well, according to the definition, this is going to be the integral from 0 to infinity of e to the minus st times t times dt. We have here an exponential function multiplied by a polynomial function. And when we want to integrate the product of two different types of functions like this, very often the correct tool is integration by parts. It's true, lazy people ride the elevator. Inverse trig, logarithms, polynomials, rationals and radicals, trigonometry, exponentials. Polynomials comes earlier, so we're going to set u as our polynomial function t. And then everything else is going to be dv. We want to differentiate u to get that du is just going to be dt. And we want to integrate dv to get that v itself is negative 1 over s times e to the minus st. Then the integral of u dv is equal to uv minus the integral of v du. So in this particular case, we have u times v, t times negative 1 over s times e to the minus st, evaluated at 0 and evaluated at infinity, minus the integral from 0 to infinity of v, which is minus 1 over s, e to the minus st, times du, which is just dt. Now from here, we play our evaluation. Remember, we are evaluating t at 0 and infinity, not s. So we plug in t equals infinity. And I know it's a little bit weird actually writing infinity on things, but it works out, and that's all that really matters. So we have minus 1 over s times infinity times e to the minus infinity. And then we have minus 1 over s times 0 times e to the 0. And I'm just going to leave the integral alone for the moment. Deal with one thing at a time. All right, here again, we have infinity to the first power. We have e to the minus infinity. We should write that out using limits, but we know the limit rule that I talked about at the beginning of this video. This whole thing is going to go to 0. In the second term, we have 0. We have e to the 0, which is 1. This whole thing is going to go to 0 as well. That really helps us out. All right. Now all we have to do is deal with the integral e to the minus st dt. Well, that's going to be minus 1 over s, which when we multiply times 1 over s is minus 1 over s squared, times e to the minus st. And we'll evaluate this at 0 and at infinity. When we evaluate at infinity, we get minus 1 over s squared times e to the minus infinity, When we evaluate at 0, we get plus 1 over s squared times e to the 0. E to the minus infinity is 0. E to the 0 is 1. All told, we get that the Laplace transform of t is 1 over s squared. I don't want to have to go through each of these, but you can go through and you can evaluate the Laplace transform for any function using that same integration technique. It's worth having these 8 as a ready reference. The Laplace transform of 1, t are special cases of the Laplace transform of t raised to the n power, n factorial over s to the n plus 1 power. Then we have the exponential. The Laplace transform of e to the alpha times t is 1 over s minus alpha. We have the trigonometric functions. The Laplace transform of sine of k times t is k over s squared plus k squared. Laplace transform of cosine of kt is s over s squared plus k squared. And then just to emphasize the relationship, the hyperbolic sine or sinh function, the hyperbolic cosine or cosh function, when you take the Laplace transform, look nearly the same, just with the addition turning into subtraction in the denominator. And the reason that it's worth having some Laplace transforms on hand at the ready is that the Laplace transform is linear. That phrase linear we have thrown around quite a bit. If anyone has taken linear algebra, you know a lot more about it. But for our purposes right now, remember that for an operation to be linear, that means if we take a linear combination, some constant a times f of t plus some other constant b times g of t, we should get out the same linear combination. A times the Laplace transform of f of t plus b times the Laplace transform of g of t. And that is going to happen directly from the properties of the integral. If I take the Laplace transform of a times f plus b times g, and I'm going to do my best to remember to keep the of t's everywhere, although suppressing of t is something that becomes more common at this point. But making sure that you can differentiate between the functions and the constants is going to get to be a little bit messy. All right, so that's the integral from 0 to infinity of e to the minus st times our function, a times f of t plus b times g of t dt. And of course, we can distribute inside of the integral. This is the integral from 0 to infinity of a times e to the minus st times f of t plus b times e to the minus st times g of t we can split up an integral over addition and subtraction and write this separately as the integral from 0 to infinity of a times e to the minus st f of t dt, and the integral from 0 to infinity of b times e to the minus st times g of t dt. We can factor a constant out of an integral. And we can recognize that these two integrals are, in fact, the Laplace transform of f of t and the Laplace transform of g of t. So this is why having that table of Laplace transforms is valuable. Because if I want to evaluate a Laplace transform of something that's a little bit messy, like say I want the Laplace transform of 3e to the 4t minus 2t plus sine of t. Well, using linearity, I can split this up. This is 3 times the Laplace transform of e to the 4t minus 2 times the Laplace transform of t plus the Laplace transform of sine of t. And if I look at my table, the Laplace transform of e to the 4t, well, alpha is 4 in this case, and we have 3 times 1 over s minus 4. The Laplace transform of t is 1 over s squared, and the Laplace transform of sine of t, k is 1 in this case, so we get 1 over s squared plus 1. We will see that it's going to be worth in the future going through the algebra and rewriting this as a single rational function. But for my purposes right now, that's good enough. I can look at a Laplace transform. I can rewrite it in pieces, and I can look up each piece on a table without having to do the integral. If this wasn't possible, the Laplace transform would not be useful. This is what makes it so we can work with the Laplace transform. Well, it's one of two things that make it so that we can work with the Laplace transform, and it's actually a useful thing to work with. The other thing, there is no indication from what we've done that the Laplace transform should be invertible. I don't have anything resembling the time to prove to you that it is invertible, but I do want you to take that on faith. I claim that the Laplace transform has an inverse. And not only that, for any function, if the function is linear, then its inverse, if it exists, will also be linear. The inverse Laplace transform must also be linear. We will denote the inverse Laplace transform as a script L raised to the negative 1 power. And the usual convention is that when we want to take the inverse Laplace transform of something, instead of surrounding it with square brackets, we usually surround it with curly braces. I don't know why that is the case, but that is definitely what I have seen most often. So my goal is to find the inverse Laplace transform of s squared plus 6s plus 9 all over s minus 1 times s minus 2 times s plus 4. And if you are stopping and saying, wait a second, this doesn't look like several things added together that we can then use the property of linearity in order to figure out. Well, you'd be absolutely right. But thinking back to previous mathematics courses, you may remember a technique called partial fraction decomposition, which we said a couple of times just never seems to go away. I have a fraction where the denominator is given to me in factored form. It must be possible to rewrite this rational as the sum of three rationals. Each one has one of these denominators. So s squared plus 6s plus 9 all over s minus 1 times s minus 2 times s plus 4 must be equal to sum a over s minus 1 plus sum b over s minus 2 plus sum c over s plus 4. Sometimes I feel like I can never get away from partial fraction decomposition. I will never say that it is fun, but it is convenient and I'm glad that it exists. If I multiply both sides of this equation by the common denominator, I turn it into a polynomial equation. I can multiply out the binomials. I can distribute the constants a, b, and c. I can group together my s squareds, my s's, and my constants. And then I can use the property of polynomials that tells us that the only way for two polynomials to be equal to each other is if corresponding coefficients are equal to each other. So my s squared terms tell me that 1 is equal to a plus b plus c. My s terms tell me that 6 is equal to 2a plus 3b minus 3c. And my constant terms tell me that 9 is equal to negative 8a minus 4b plus 2c. I've got a couple of options on how to combine these from here, but Using the process of elimination, if you've studied linear algebra in the past and you're comfortable with Gauss-Jordan elimination, it's a lot less writing. But if I take the second equation plus 3 times the first equation, I get an equation that does not have C. And if I take the third equation and I subtract twice the first equation, I get a new equation that does not contain C. Very conveniently, if I add my two new equations together, I get the value of A. Then if I take that and I plug it into one of the other equations, I get the value of B. And then if I take those and I plug it into one of the original equations, I get the value of C. Right. So now I can take this Laplace transform. Instead of worrying about the single fraction s squared plus 6s plus 9 over s minus 1 times s minus 2 times s plus 4, I can break it into pieces. I have A, which is negative 16 over 5 over s minus 1. I have B, which is 25 over 6, all over s minus 2. And I have C, which is 1 over 30, all over s plus 4. That now finally looks like something we can sink our teeth into. So using the properties of linearity, I can split this up and I separately have negative 16 over 5 times the inverse Laplace transform of 1 over s minus 1. I have 25 over 6 times the inverse Laplace transform of 1 over s minus 2. And I have 1 over 30 times the inverse Laplace transform of 1 over s plus 4. Looking it up on the table, 1 over s minus alpha is what we expect to get out of the Laplace transform of an exponential. So this first one is the exponential function when alpha is 1. negative 16 over 5 times e to the t. The second one is the exponential function when alpha is 2, 25 over 6 e to the 2t. And the third one is the exponential function when alpha is negative 4. So 1 over 30 times e to the minus 4t. All right. Deep breath. We got there. That's the basic idea of these. I'd like you to try something in the forward direction, not in the reverse direction. But I'd like you to take the Laplace transform of t squared minus 3t plus 5. Definitely easier than the last one we went through. But again, make your life easier on yourself. Use the linearity and the table of Laplace transforms. Do not try to set this up as an integral. It's not worth it. We will come back and revisit that integral in some of the homework problems where I'm going to ask you to verify some of the formulas on that table. But for right now, this is good enough. All right, take a few minutes on that one, see where you can get to with it, and I'll see you in the next video.